Well, welcome to the video. Uh, Today we're going to look at 7.3, where we're going to look at special products of polynomials. So, the central question that we're looking at is, what are the patterns in the special products? The patterns in a special product for polynomials are, we have first what is called a sum and difference pattern, where you have the exact same terms in the first and last of each set of parentheses. The only difference is one is plus, one is minus. And the other two are perfect square binomials, and one being a perfect square where it's plus, one being a perfect square where it's minus. So we have uh, formulas for these for these patterns. First off, if you look at the perfect square binomials, we have a pattern. If you have a plus b quantity squared, the result of that is going to be a squared plus 2ab plus b squared. If you have it as a subtraction, the only difference is the 2ab is subtracted, everything else remains the same. And when you're looking at a sum and difference pattern, what you are essentially doing is squaring A and squaring B and putting subtraction in between them. Basically, what we can say is where we come up with these formulas is either from the multiplication of the two binomials, because essentially you could say, well, a plus b quantity squared is just a plus b times it by a plus b, and you can FOIL it out from there. A times a is a squared, a times b is plus ab, b times a is plus ab, and b times b is plus b squared. We have the exact same variables with the exact same degrees, which means that we can say that it is 2ab, so it's a squared plus 2ab plus b squared. Anytime that you have these patterns, you can use the formula, or you can just expand. This is the expanded portion of a perfect square, and multiply like we did in the previous section. All right. Either way, I have uh, I have no issues with either approach. So you could, if you look at it, I'll do example A both ways, and we will get the exact same result. So this here, 3x is going to equal A, and 4 is going to equal B. All right, this, if this is A plus B, and this is quantity squared. So using the pattern of a squared plus 2ab plus b squared will give us this. A squared, all right, is going to be 3x. So 3x squared is going to be 9x squared plus 2 times a, which is 3x, times b, which is 4, plus b squared, which is 4 squared, which is 16. The only thing you got to do now is multiply everything in the middle term. And once you do that, you get 9x squared plus 2 times 3x is 6x. 6x times it by 4 is 24x, and plus 16. So we should get the exact same thing if we try to expand this. So if we expanded this, we get 3x plus 4 times by the quantity of 3x plus 4. looking using the FOIL method, you can also make a table too if you'd like. So this turns to 3x times 3x, which is 9x squared. 3x times 4 is plus 12x. 4 times 3 is plus 12x. 4 times 4 is plus 16. Add these two together, so I got 9x squared plus 24x plus 16. Is this the same as this? Absolutely. So there's no difference in the approach, still get the same result. The majority of you will probably go with expanding and foiling. Majority. So with that being said, let's expand 5x minus 2y quantity squared. So that's just going to be 5x minus 2y times by the quantity of 5x minus 2y. And we FOIL it out. 5x times 5x is 25x squared. Outside terms is going to give me a negative 10xy. Inside terms is going to give me a negative 10xy. And then finally it's going to be plus 4y squared. Combined the like terms in the middle, 25x squared minus 20xy plus 4y squared. So again, I would encourage you to practice these problems here. If you have questions on them, please comment down below. But let's see if we can find a sum and difference pattern, which we have right here. We have the exact same values, t and 5, t and 5. The only difference is one's positive, one's negative. This one here, you're more than welcome to FOIL it out. This one, I would say, personally, I would love using the formula. But let's FOIL it out first. So t times t is t squared. T times negative 5 is negative 5t. 5 times t is plus 5t. And 5 times negative 5 is negative 25. All right, this is why I prefer using the formula, is this gets canceled out because they're opposites. So I'm left with t squared minus 25. So what I like to do is, all right, they're both t's, square them together, you get t squared. 5 and 5, square them together, you get 25, and I know there's subtraction in between them. That's why I prefer that. So 3x and y, one's positive, one's negative. I know it's a sum and difference pattern. So I can say, okay, what is 3x squared? Well, 3 times 3 is 9. X times x is x squared. Y squared is the square of that, subtraction in between them. Now here, it says use special products, special product patterns to find the product of 26 times 34. Here's what they mean when they say using the special products. So you're going to use one of the three formulas to help you solve it. So what you're going to take a look at is what can you, what value could you use to commonly share a value that's going to get you both 26 and both 34. So what this means is this. I can rename 26 and call it 30 minus 4. I could rename 34 by saying 30 plus 4. And if you notice, 30 and 30, 4 and 4, I can now use the sum and difference pattern to help me find the product of this. So I can now go 30 minus 4 times by the quantity of 30 plus 4. So all we have to do now is take 30 squared, which is 900, subtract it by 4 squared, which is 16, and then I take 900 minus 16, and we get 884. So I would say that hopefully you should have a pretty good grasp of sum and difference patterns here, here, and here. But let's take a look again at this uh, special pattern here. It says they want us to describe 21 squared. So what we're going to do is we're going to rewrite this as 20 plus 1 because you can easily square 20 and you can easily square 1. So it's going to be 20 plus 1 quantity squared. Now you can use the formula, a squared plus 2ab plus b squared, or you can expand it like this and then FOIL it out. So 20 times 20 is 400, plus 20 times 1 is 20, plus 1 times 20 is 20, and 1 times 1 is 1. And you can just add these all up. So 400 plus 40 plus 20 is what, 441? And you can check it by taking 21 squared in your calculator, and it is that result. All right, so we have this story problem here. It says a combination of two genes determines the color of the dark patches of a border collie's coat. An offspring inherits one patch color gene from each parent. Each parent has two color genes, and the offspring has an equal chance of inheriting either one. So here it says the gene B is for black patches and the gene R is for red patches. Any gene combination with a B results in black patches. Suppose each parent has the same gene combination BR. It says the Punnett square shows the possible gene combinations of the offspring and the resulting patch colors. So B and R, B and R. So B times B is B squared. Basically, over here, B times R is BR. On the bottom left, B times R is BR. And then finally, R times R is R times R squared. So here it says, what percent of the possible gene combination results in black patches? So basically, since these are all the same, you have a 25, 25, 25, 25, and 3 of them are black patches. That tells us that we have a 75% chance of it resulting in black patches. Here, it wants you to show how to use a polynomial to model the possible gene combinations. So here is how we go about doing that. So if each dog has half of it as a black patch gene and half of it as a red patch gene, you could rewrite this as 50%, which would be 0.5b plus 50% or 0.5r, and that would be quantity squared because of how the Punnett squared model is illustrated. So again, you can use the formula or you can expand and FOIL it out. So this would be 0.5b plus 0.5r times by 0.5b plus 0.5r, which then, when you solve it out, becomes 0.25b squared plus 0.25br plus 0.25br plus 0.25r squared. I have like terms in the middle. So my simplified expression will be 0.25b squared plus 0.5br plus 0.25r squared, which basically means that if they were both had, um, so you have 25% of both black patches, you have 50% of them as black and red patches, which would still be black patches because of what the problem stated, that whenever you see a black gene, it uh, supersedes the red, and then you have 0.25 double red. And that is being able to um, use special product polynomials. Hope this helps. Until next time.